All right, everyone. Yesterday, we introduced Coulomb's law, which started with a little bit of an analysis of Coulomb's torsion balance experiment, which I'll repeat very briefly here. Coulomb's torsion balance experiment essentially consisted of two charges on the end of a rod hung by a string from a ceiling or a roof or whatever. One of those objects on the end of that rod had a charge. We'll call it charge 1. We bring another object nearby that is charged. We'll call it charge 2. Charge 2 is going to either attract or repel charge 1. We don't know what yet. We don't know whether it's going to attract or repel. Depends upon whether charge 1 and 2 are positive or negative, or one's positive, one's negative, or both positive, whatever. Doesn't really matter. That's neither here nor there. Okay, what matters is that there is a force. And that force of attraction or repulsion causes the string to twist, just like a force on a swing set does when you're twisting a swing set around, ready to let it go so you can spin around, right? We've all been on that swing set before where we turn the swing set, we turn it, 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 and then we let it go so that we spin around really, really fast. We know that when we turn it more and more and more, it requires more and more and more force. We could measure the force that's required to turn it a certain amount. Coulomb would have known how much force is required to turn or twist this string a certain amount. Therefore, when he observed how much charge 1 deflected, or how much the string twisted as a result of the deflection caused by number 2, we could determine the force. He could also determine the distance separating charge 1 and charge 2 pretty easily with a ruler. He could also determine not the charge of object number 1 and object number 2, but rather the relative charge. So in other words, if it started off as Q, maybe it's a half Q next time. Maybe it's a quarter Q next time. Maybe it's an eighth Q or a 16th Q next time. He could determine the relative charge, which is good enough for determining a relationship. He's able to measure all these things. So he starts performing 3 separate experiments. The first experiment, he would manipulate Q1. He would see how F responded to that. The force of attraction or the force of repulsion would respond to that. He found that he got a straight line. That told him that F was related to Q1. Yesterday afternoon, somebody said, what does that symbol right there mean? Nobody asked me that yesterday morning. Hey, what does that symbol right there mean? You guys tell me, what does that symbol right there mean? Have you guys learned about that in math class? Proportionalities? No? It means that it's related to. So in other words, if F is proportional to or related to Q, linearly related to Q, then whatever happens to Q happens to F. If Q doubles, then F doubles. If Q goes down by a factor of 16, then F goes down by a factor of 16. They're directly proportional. By the way, what variables would I have to keep constant in this experiment? What would be my control variables here? If I change Q1 and F responded, what has to stay the same? Well, give me one that has to stay the same. Good, Q2, and the other one would be distance. The distance that separates them are. All right, so then he manipulates Q2, keeping Q1 and R constant. It also ends up being a straight line. So therefore, the relationship between F and Q2 is also a linear relationship. If Q2 goes down by a factor of 26,150, then F goes down by a factor of 26,150, right? They're linearly related. Whatever happens to Q2 happens to F. Finally, he performs his third experiment where he changes the value of R. This one produces a graph that looks like this. That's not a linear relationship. In fact, as R goes up, F goes down. But it's not a linear decrease in F as R goes up. Rather, as R goes up, F goes down by a squared factor. So in other words, if you double R, F goes down by a factor of a quarter. If you quadruple R, then F goes down by a factor of 1/16. It's an inverse square relationship, we call it. Now, Coulomb comes along and he sees his results here from all three of these experiments. He puts them together. Says that F is related to Q1, Q2, right? Directly related to Q1, directly related to Q2, and it's inversely related to R squared. But if you had learned about proportionalities in math class, you would have learned that you can't just say F is equal to that. The F is proportional to that. If F is proportional to that, then it's got to be equal to a constant, a certain constant value times that. That constant that we call Coulombs constant. That has a value, if you remember this at all from yesterday, is 8.99 times 10 to the 9 Newton meter squared per Coulomb squared. You don't have to remember that number. It's on your data sheet, of course. Just know where to find it, bless you, on your data sheet. All right, we also compared this equation that we learned yesterday for the first time to an equation that we saw last year. G m1 m2 over r squared. That's Newton's law of universal gravitation. There's some pretty big similarities. There's some pretty big differences as well. The similarities? Well, the structure is the same. We call them both what? We call them both inverse square relationships because F is inversely related to the square of the distance. They're both inverse square relationships. They both have the same structure. Look, it's a constant times Q1, Q2, M1, M2 over the distance squared. Differences? Well, the first difference is, big difference is the value of them. Which one's a bigger force? Like, and by bigger, I mean way bigger. Which one's the bigger of the two forces generally? All other things being equal, the Coulomb's force, the electric force is going to be bigger. We know that because the value of K is 10 to the 9 Newton meter squared per Coulomb squared, whereas the value of G is 10 to the minus 11. It's 10 to the 20 times smaller. And then finally, the final difference between the two is that gravity, we always know, is an attractive force. Mass pulls mass together. But charges don't always pull charges together. They sometimes do, but they sometimes push them apart. Depends upon what kind of charge you have. You don't get that issue with gravity, right? Because you only got one kind of mass. It's mass. Right? It's just mass. But charge, you can have both positive and negative charge. Right, Devin? Let's take a look at our first mathematical example of the unit, other than simply averaging two charges together, which we did last week. This one is a Coulomb's law problem. 10.1, you see that we're in chapter 10 now, if you haven't got chapter 10 downloaded, page 530. It says a small metal sphere with a negative charge of 2.10 times 10 to the negative 6 coulombs. Listen, we talked a lot last unit about underlining, circling, highlighting, things that may lead you to make a silly mistake. Whenever we see a negative charge, I would suggest you do that. Now, in this particular question, you're going to see that it's not really going to matter. You're not going to make a mistake if you forget to circle the word negative there. It's not going to change a thing. But in some questions, it will. If some questions you miss the negative, you're going to make a mistake on it. So we've got a small metal sphere with this negative charge of 2.1 times 10 to the minus 6 is brought near an identical sphere with a positive charge. I'm just going to circle that as well just to remind me that it's one's positive, one's negative. If they're both positive, yeah, I could probably get away without circling it. So the distance between the centers is 3.30 centimeters. Calculate the magnitude and the type, attractive or repulsive, of the force of one charge acting on another. So let's write down some givens here. We'll call this Q1. We'll call this Q2. We'll call this what? This distance that separates the centers of the spheres is going to be what variable? Good. We'll call it R. Let's not say radius, because radius infers that it's going in a circle. And it is possible that you get a question where the charge is going in a circle, right? The electron orbits around the nucleus in a circle. If you're finding the force of electricity between the electron and the nucleus, then R would be the radius. but it doesn't have to be a radius. Okay, but I know exactly where you're coming from there, Simon. The symbol is R, right? It infers radius. If it was me that made up the symbols, I would have called it D for distance. Some textbooks you see will call it D, but our diploma exam people call it R, so that's what we're going to call it. We're going to find the magnitude and the type of force here. So let's find the magnitude first. The equation will give me the magnitude, not the type, not attractive or repulsive, just the magnitude. But that's okay. Okay, we can figure out whether it's attractive or repulsive later on. KQ1, Q2 over R squared. K, you're probably not going to remember this number yet, but it's on your data sheet. 8.99 times 10 to the 9 Newton meter squared per Coulomb squared. Which charge is which? Which charge is Q1? Which charge is Q2? 2.1 or 1.5? Let me ask you this question. Kirsten, what's 1 times 2? 2. Very good. Emma, let me ask you this question. What's 2 times 1? You guys are amazing. 1 times 2 is 2. 2 times 1 is 2. It doesn't matter what order we multiply things in, right? 2.1 times 1.5 or 1.5 times 2.1, exactly the same thing, right? So call whichever one you want charge 1. Call whichever one you want charge 2. Hey, I've already called this one charge 1 and this one charge 2, but if you did it opposite to that, then that wouldn't be a big deal. One thing you do have to remember, though, is convert that R to meters, 0.033 meters. Have I missed anything? Simon? Yep. Well, okay, that's a good question. Do I always have to put the absolute value sign around the force? If you don't put the absolute value sign around the force, it's not the end of the world. Okay, if you leave that symbol of absolute value off, it's not the end of the world. But understand that when you solve for the force, you're not going to get the direction. It's always going to be the absolute value. Now, it's a vector. Force is a vector, always. There is a direction associated with it, but in this case, the equation doesn't tell me the direction. And that's why I put the absolute value sign around it. But in the end, if you leave that off, what's going to happen? Well, you're going to get the same answer as me. You're just going to have to remember that it doesn't include direction. Okay? Guys, have I left anything off here? Have I missed anything? I was waiting for somebody to tell me that I should have put a negative in for this, right? It's a negative charge. But nobody did tell me that. And that's kind of good because I don't put the negative in there. For us, in an equation, negative will always mean direction. Negative here doesn't mean direction. It means a type of charge. So I don't want you to ever plug a negative for a charge into an equation. Ever. For any equation. This one or any of the other ones that we'll learn in the future that involve charge. Don't put the negative into the equation. Now, why did I bother circling it if you're never going to put it into the equation? Well, because sometimes it matters in the question, just not in the equation. So let's get the value of F here. Let's pull out the calculator just to make sure that everybody can do this. So we're going to say that constant 8.99 times 10 to the 9. Notice they give us the charge in coulombs here, but 2.1 times 10 to the minus 6 coulombs is actually 2.1 micro coulombs. And you'll often see that written as micro coulombs. Right? We said a coulomb is a really, really big unit of charge. So typically you are dealing with micro coulombs or nano coulombs, 10 to the minus 6, 10 to the minus 9 coulombs, not coulombs, because it's just too big of a unit. 1.5 times 10 to the minus 6. Let's divide that by, and be careful here, 0.033 squared. We get 26 newtons. 26.0 newtons, it should be 3 digits. All right, the second part of the question is it attractive or repulsive? Everybody know the answer to that question? The equation has not told me whether it's attractive or repulsive. It never will. So how do I determine whether it's attractive or repulsive? I'll give you a hint. It's a really, really easy answer. Ken? How do you know? Right. One's positive, one's negative. Opposites attract, right? We don't need an equation to tell us that. We just need to recognize that one is positive and one is negative. Not a crazy hard question, I don't think. Here's a pretty common mistake, though. Here's something that we see often, and I guarantee you, if this appears as a multiple choice question, which you should be happy if it does. You should look up and say a little prayer of thanksgiving if it does, because it's a pretty easy question, right? But a common mistake, and I guarantee if it appears as a multiple choice question, one of the options will reflect this mistake. This. Here's why. We have an exponent, 10 to the 9, another exponent, 10 to the negative 6, another exponent, 10 to the minus 6. Then we divide by, and sometimes we have to convert from centimeters to meters. You type all of those things into your calculator, and it's so easy when you get down to that last thing of squaring that distance to just forget to put the square on there. Just go KQ1, Q2 over R. Even if you've written down the equation properly, we still sometimes forget to square that R. Be careful of that, okay? I'm telling you, you might not do it, but a lot of people do make that mistake, and it's a silly mistake, and we don't want to get a question wrong because of that. Okay, one question. Wow. Easy. Let's give it a try here for the next 3 minutes or so here, guys. All right, if we have no issues with the question on page 530, let's take a look at one more here. So the two spheres in example 10.1 are momentarily brought into contact with each other and then returned to their original separation distance. Determine the electrostatic force now exerted by one charge on the other. Isn't it? Interesting. Let's go back to that question here. We had the example negative 2.10 times 10 to the minus 6. That was Q1. Q2 was positive 1.50 times 10 to the minus 6. And the distance that separated them was 0.0330 meters. How is this question different than the example question that we did? Back in example 10.1, we multiplied those two charges together, multiplied it by k, divided it by r squared, and we got our answer. How is this question here any different? Just because we touch them together, where are we here? Just because we touch them together, how does it make the question different than our last example? Emma, it looked like your hand was kind of starting to do something there. No? Anybody have an answer for me on that? Here's what you got to look at, you guys. There's a then here. This happens, then this happens. That's two different things. That's two events. They touch together. Stop. Pretend the question's over. They touch each other. The question's over. Well, when they touch each other, what happens to them? They want to balance out. Then they're brought back to their original separation distance. So now their charges are different than they were before. Now they're balanced out at a distance of 0.0330 meters apart. Always remember that. If you see the word then, or even something that's like the word then, two events happen, then treat it as two separate problems. Touch them together, balance them out just like you did earlier on in this unit. You guys were great at that. And then find the force, just like you did in the last question, which, again, you guys seem to be good at. So let's touch them together first. When they balance out, it's negative 2.10 times 10 to the minus 6 plus 1.50 times 10 to the minus 6 divided by 2. What does that give me for a charge on both of them here? Negative 0.6 or negative 3.0 times 10 to the minus 6? That's not right. 7? Is that right? That's the charge on both of them, right? That's going to be Q1 and Q2 after we touch them together. Now, it's a pretty easy problem, right? Knowing what charges I should use, KQ1, Q2 over R squared. It's my constant again that's on my data sheet. Notice again that have dropped the sign of the charge, because the charge for us, sorry, the sign for us, a negative for us will always indicate direction, not a type of charge. Let's figure this one out on the calculator. And we get 0.743. We're not asked to determine whether it's attractive or repulsive. Who could tell me, though, whether it is attractive or repulsive in this case? No, it's going to be repulsive. Why is it going to be repulsive? When they touched each other, they balanced, they both became negative. So one was a positive. Think about this. One was a positive. Look at my hands up here. This hand's positive, this hand's negative. They're attracted, right? They're attracted. They're attracted. They're attracted. Then they touch. Then they balance out. Now what happens? Because they're balanced out in like charges, they repel, they repel, they repel. So there's an initial attraction. They touch each other, and then they repel each other. Does that make sense? I got a question for you. Why, when you rub a balloon against your hair and you stick it on the wall, does it actually stick to the wall? As opposed to, well, shouldn't it be attracted to the wall, but then when they touch each other, the charges transfer and they balance out and then be repelled from the wall? What's a balloon made out of? Latex or rubber? What's a wall made out of? Drywall, wood? What are characteristics of rubber and wood versus, say, aluminum and steel and copper? Rubber and wood are insulators. So when you rub that balloon against your hair and put it against the wall, are you going to transfer charge? Sure you are, sure. But it's not going to be nearly as quick and not nearly as effective. So when you put that balloon against the wall, it's not going to balance out right away. It's going to stick to the wall, initially at least, because you've got that charge on the balloon and that neutral wall without the transfer taking place so quickly as you would with conductors. Okay, let's try this question. Okay, let's spend a couple minutes just going over page 531 here. A metal sphere with a negative charge of 3 microcoulombs is placed 12 centimeters from another sphere that's positive 2 microcoulombs. So we get the negatives, the positives there. We want to draw attention to that because clearly when we're touching two things together, which we're going to do in this case, it's important whether they're negative or positive. If they balance out, we want to average them out. We got to make sure that we know whether they're negatives and positives before we balance them out. So we touch them together. We want to find the force that acts between the two. Let's get Q1 here. In order to get Q1 and Q2, we're going to start off by averaging those two charges together. 3.00 microcoulombs plus positive 2.00 microcoulombs. Divide that by 2, gives us a charge of negative 1 divided by 2, so negative 5.0 times 10 to the minus 7 coulombs. Okay, that's going to be Q1. That's going to be Q2. The distance that separates them, 0.12 meters. Okay, we want to convert the centimeters to meters. Let's find the force. Notice, listen, I don't know if anybody caught this or not. You didn't really need to catch this to do this question, but notice it does say 2 metal spheres. Why do you think they're saying 2 metal spheres as opposed to, say, 2 plastic spheres? When they touch each other, what's going to happen really quickly if they're 2 metal spheres? The charges are going to transfer, right? Because they're conductors. So they're going to balance out. We know they're going to balance out more or less when they're metal spheres, when they're conductors. So F is equal to KQ1, Q2 over R squared. That means it's a big long constant again, 8.99 times 10 to the 9 times 5 times 10 to the minus 7. Oh, okay, I ran out of space. Can I do this? Okay? Sure I can, right? It's the same number. It's not always going to be the same number, but when they're touching together, it is. So I'll do that just to save a little bit of space there. R is 0.12 meters. So do not forget to square that. And let's pull out the calculator here. Some people, when they see this number so often in this unit, 8.99 times 10 to the 9, they like to program it into your calculator. Is that okay to do? Sure it is. But what's going to happen come to poem exam time? Your calculator is going to get cleared, right? So don't get too used to having that number programmed into your calculator because it's not going to be there come exam time. We do that math, we get 0.156 or 1.56 times 10 to the minus 1 newtons. Listen, it says repulsion here. How do we know it's repulsion? I'll tell you what, whenever you get one of those questions where they touch each other and then they spread apart, it's always going to be repulsion because when they touch each other, the charges balance and they're both going to be negative or positive. Both can be like charges. Hey, quick question here. If they asked you to express this as b times 10 to the negative w, what's the value of b? What would be my answer? How would I express that? 1.56. If they asked me to express that as a decimal bc times 10 to the negative d, a, b, c, d, what would be my answer? 1, 5, 6, 1. Okay. So there's a couple ways they could ask us to express that answer. Okay, I want to look at a multiple choice question here, which is real similar to what you've just been doing. Multiple choice number 42, or I should say numerical response number 42. We won't bother submitting this one. Just do this one at your desks, and then we'll take a look at it as a second in a group, okay? Okay, so listen, we got one of those then questions. Something happens, then something else happens. They touch each other, and then they're separated. We want to find the force. Microcoulombs, negative, microcoulombs, centimeters. Let's balance them out first. Okay, we got 4.50 microcoulombs plus negative 2.40 microcoulombs. Divide that by 2. And I think when we do that, we end up getting 1.05 microcoulombs, or 1.05 times 10 to the minus 6 coulombs. That's for Q1 and Q2. The distance that separates them is going to be 0.0250 meters. We want to find the force, just like it was in the last couple of questions that we've done. 8.99 times 10 to the 9 times this again, divided by this squared, gives me an answer of, what was it, Daniel? Yeah. Uh, 2.1? Well, when we add these up, we add this up, it's 2.1, right? But then you got to divide it by 2, right? Make sense? Does that make sense, guys? Who's got an answer there for that? Yep. 15.9. Who got 15.9 for that one? Okay. How many people forgot to divide by 2 there? Listen, if that was multiple choice, that would be one of the options, right? Because that would be a pretty common mistake. How many people didn't square? Anybody not square the distance? A couple mistakes there. Okay, both silly mistakes, right, that we can fix come test time, right? So we don't have to make those mistakes again. All right, not too bad, I don't think. How about this one? Actually, let's not do that one. Let's do this one, 10.4. Says a small metal sphere with a negative charge of 2.1 times 10 to the negative 6 is placed midway between two others. Uh-oh. Sphere B, negative 2.10 times 10 to the minus 6, is placed midway between A and C with positive charges of 1.00 times 10 to the minus 6 and 1.50 times 10 to the minus 6 coulombs, respectively. The three charges are all along the same line. What's the net force on the negative charge? In other words, what's the net force on this guy right here, charge B? Any ideas there? Yep, Simon? Okay. Okay, so find the force between A and B, and then find the force between B and C, and then what do you do with those? Okay, so take the difference or add them together or something like that. What we got to do before we actually find the values of both of those forces, ladies, is draw what we call a free body diagram. You do like hundreds of free body diagrams in Physics 20. Okay, so this is nothing new. A free body diagram shows forces that act on the objects. It's important to draw the free body diagram so that, Simon, when we go to add these together, exactly what you said to do, we know which way to add them, okay, whether they're right or left, and therefore either positive or negative. Maybe they're both positive, all right. Maybe one's positive, one's negative, all right, two different answers, right? So we got to make sure that we draw that free body diagram so that we know that. Let's pretend C's not there for a second. A and B are the only ones there. Do they attract or repel, A and B? Is that attractive or repulsive? Kristen? It's attractive. One's positive, one's negative, it's attractive. That means that A is going to be pulled towards B, and B is going to be pulled towards A. But I don't really care what happens to A, because that's not the question. Okay, it is pulled towards B, but it's irrelevant because that's not part of the question. We want to know what happens to B. Now pretend A is not there. B and C, positive and negative, do they attract or repel? They attract as well, right? One's positive, one's negative. That means if they attract, then B is pulled towards C, and C is pulled towards B. But I don't care what happens to C, because that's not part of the question. So even though it is pulled back towards B to the left, it doesn't really matter, because the question asks us what happens to B. We're going to call this one the force of A on B. We're going to call this one the force of C on B. You can call them whatever you want, really. That's what I'm going to name them. Force of A on B and the force of C on B. Now, as Simon said just a minute ago, let's get the values of both of those forces. That's easy. Okay, that's the very first example problem that we did in this unit earlier today. Just calculate Coulomb's law force. We'll call it KQA QB over R squared. Let's get both of those values. Notice again, I'm dropping the sign of the charge. For us, a negative in an equation is always going to mean direction, left, down, south. It's not going to mean a type of charge. The distance that separates them, oh, do we know the distance that separates them? Okay, A and C are 3.30 centimeters apart. That means that A and B, since they're midway between there, 1.15 centimeters apart. And B and C are also 1.15 centimeters apart because the distance between A and C is 3.3. All right, so let's put that in now. Let's make sure we put it in meters, though, 0.015. Do the math on that one. 48.346 newtons. Let's do the same thing for the other force, the force of C on B. There's my fab force, FAB, and then there's my force, FCB. KQC QB over R squared. Okay, there's a mistake in this one. Simon, what'd you get, 142? 8 newtons. And what did we get for the second one? 214 point, what? 214.13. Never mind. I got it. Don't worry about it. I got it. 214.13. Okay, so what do I do with these now? Almost there. This is when it's really important to have that free body diagram drawn. FAB is a negative value because it's to the left. 142.8 newtons. FCB is a positive value because it's to the right, 214.13 newtons. And when we add those together, we're going to get about 71.4-ish. 71 point something. 0.8. It's not 0.8. $71.3 newtons. And it's positive, which means it's to the right. So not a crazy question either. It's more difficult than the questions you've just done because there's extra work. But in the end, it's still just get this force, add them together, but you have to have that free body diagram drawn so that you know whether to add them together as positives or negatives. All right, that's pretty much it for the day for us. We do have some homework to do, and the homework that we want to do, page 533, I'm going to give you question number 1. Number 2, if you really want a challenge question, try question number 2. It's a good one. Okay, but it's beyond what you would have to do on a unit test or a diploma exam, but it does get the mind thinking. All right. In addition, I will assign the following for Thursday. This is for tomorrow. For Thursday, I want to assign worksheet number 6. All right, you can take the rest of the class and work on both of those now.